3. Central tendency. Some of the learning objectives in this chapter we're going to go over include, well, 1, the purpose of measuring central tendency, or the average, medium, or center. We're going to define and compute 3 different ways of measuring central tendency. We are going to draw and interpret graphs displaying mean, median, mode, right? All the different ways we can represent different treatment or condition groups. Again, always trying to find that average or that group or that middle. 3 different measures of central tendencies, looking at both skewed and symmetrical distributions. And then we're really going to hit hard when you mess with the mean, right? So describing how the mean is affected when you mess with the scores in the distributions. Some things to keep in mind from the previous couple lectures are the summation notations, right? So sum of, or that beautiful looking E symbol, X equaling the scores, F being the frequency, that type of stuff. And then everything that we talked about last lecture, the frequency distributions. Okay, so if we were to talk about central tendency and what does that mean, the whole goal of central tendency is to find that single score that really defines what is the center of that distribution. So if you were to take a look at all the different scores all put together, and if someone was to ask you, well, what is the average, what is the middle, what is that one score that really stands out and defines the capture, the average, the standard, right, average or median or middle of that whole grouping, what would that be? That would be the central tendency. Yes, it is a statistical measurement, and the purpose is to find the single score that's the most typical, most representative of your entire group, or out of all your entire population, or out of all of your sample that you did your study on. Okay, so take a couple seconds to look at these different frequency distribution graphs here, right? So you have graph A, you have a perfectly symmetrical distribution there, right? So in these 3 distribution graphs, you might have a little bit more of a difficult time describing what the center is. So A is pretty simple, right? If I was to ask you, okay, you had a bunch of scores in your study there, right? You're looking at cognitive behavioral therapy, and you were doing you were doing a certain analysis, and the average. If I was to ask you, okay, what did the average person give you for a score? Where did the scores pile up in? Well, in that first one there in A, you would say around 5, right? So again, keep in mind the F represents the frequency, or the number, or occurrences, or count. Right? So the center, or the most reoccurring, right? See, in that symmetrical one, it kind of peaks at 5 and then kind of comes back down. Yes, you had some people give you a score of 2 and 3 and 7 and 9, but the most, right, the most reoccurring was 5. But if you take a look at the graph there over on the far right-hand side, in the right upper right-hand corner in B, it gets a little bit different, right? So now we have a negatively skewed distribution, right? So think that the scores are piling up on the right-hand side and the tail is pointing over on the negative side, that number line. The most reoccurring, or the mode, is 8, but is that the most representative? I don't know. You had quite a number of people that scored well below 8, right? You had a group of people that scored a 1 and a 2 and a 3 and a 4 and a 5. So telling people that the 8 is a central tendency, that might not be 100% accurate. And then what if you have a bimodal distribution, right? So take a look at the bottom right-hand corner there, right? So anytime you have a bimodal or trimodal distribution, picking one side or the other also might not be accurate or fair representation. Right, so in a bimodal distribution, this is your classic, online grade distribution for courses, right? So A's and F's. Giving the answer of A or an F is wrong, right? Also giving the answer of C is wrong, right? So there's different distribution shapes that require different ways to find the center. Okay, so like we introduced in last lecture, right? So we did have different equations for when we're determining population versus sample. Okay, so the equation you see there on top is for the population, and when we're determining mean for a population, it's going to be that beautiful Greek letter mu, right? So mu equals sum of x, and x being your scores, right, divided by n, and capital N, like we learned in the last lecture, tells you that we're dealing with a population. Mu also tells you that we're dealing with a population. Take a look at the equation now below. Determining a sample mean is mean equals sum of x divided by n lowercase n. So yes, written out like English, like words, right? Sample mean. Or if I just show you M, capital M, that should tell your statistical brain, okay, you're asking me to find the mean for a sample. Okay. A silly way to remember it is mu is larger, like a cow is larger. So, and mu kind of sounds like what a cow sounds like, right? So mu. So again, I know, silly, but you'll probably remember it. Okay, some of the definitions. So some of the definitions for the mean is you're dividing the total equally. It is a balance point of your total grouping of your scores, right? When we talk about balancing the point, it is the value of the mean will always be located somewhere between the highest score and the lowest score. That makes sense, okay? When we talk about dividing the total equally, we're talking about both the sum of scores is equally divided by the number of scores and the amount each individual gets when the total is divided equally among all the individuals or participants in your study. This is what it looks like kind of graphically. Okay, so as you can see here, we're dealing with a histogram. So think back to last lecture, histogram, because you know that those 1 and 2 points are kind of mushed up next to each other. So, and we're dealing with a population, because if you look down there in the triangle, we have that Greek letter mu, not a big letter M. So what we have here, though, in our raw scores, we had, we'll just say like one person scored a score of 1 and one person scored a score of 2. We had 2 people score the score of 6, right? And then over on the far right-hand side there, we have one person score a 10, okay? Depending on the frequency, because we had 2 people score a 6, one person score 10, right? So when we're talking about balance point, we have to keep in mind our frequency, right? Weighted mean. When we're dealing with adding up and trying to find average or mean of different groups, right? We have to determine the weighted mean. Okay, so definition-wise, a weighted mean is when you combine 2 sets of scores or more, and then you find the overall mean for the combined groups. This is very important when you're dealing with trying to find the average and you're dealing with different sized participant groups. Okay, for example, if I say I have a great new therapy, right? A therapy trick or a therapy strategy that is going to help people lower their test anxiety, okay? And my therapy strategy is as you're taking the test, you need to chew gum because that mimics eating. And physiologically, what eating does is, or chewing gum is, right, so it tells your brain, okay, I'm macerating my food, all right, I'm producing saliva, I'm swallowing, and so what that's telling your brain is I'm eating. Well, physiologically and psychologically, what I'm interpreting that to be, right, on a psychological scale, is I'm in a state where I'm relaxed enough to eat. I'm not being chased by a bear. I'm not drowning. I'm not asleep, right? I'm in a certain state, homeostasis-wise, that I feel safe enough to eat. I feel surrounded by people that I'm okay to eat with, right? I feel like the food is safe, right? So physiologically, I'm going to relax. My blood pressure is going to lower. My breathing is going to regulate, right? So chewing gum mimics eating. If you can eat while you're taking a test, it actually works a little better, but chewing gum will be enough, okay? So if I have 5 groups and I give each one of my groups chewing gum, right? And in one group I have 10, another group I have 9, another group I have 12, and another group I have 7, another group I have 13, and in my last group I have 100, right? Feel how alarm bells kind of went off in your brain there? That group of 100 should weigh more, right? Should take more space, should be heavier in my overall results, because they're almost 10 times the size as all my other groups, right? So when we talk about weighted mean, what we're doing is we're giving space, we're giving weight proportionally. Okay? So if I find that for whatever reason, yes, chewing gum does lower test anxiety, right? In group 1, 2, 3, and 4, in my group that had 7 and 10 and 12, and it didn't in my group that had 100, we got a problem. Because it's like if you dump them all into one bucket and then averaged it, versus if you just counted them each as one, right? You have to give that group that has a lot more people in it more of a say. Okay, so we do this in 3 steps. Okay, step 1, you determine the sum of all the scores. Then you determine the combined number of scores. Then you divide the sum of scores by the total number of scores. Okay, mathematically it sounds like this. Mean equals, or the weighted mean equals, sum of x for the first group plus the sum of x for the second group. And I'm just going to use 2 sets of scores for this one. But in theory, you can keep going. So if I had 3 groups or 4 groups, it would then be plus sum of x for the third group plus sum of x for the fourth group, right? So you get it. Divided by the number of people in group 1 plus the number of people in group 2 plus, and then you keep going again, depending on however many groups you have. That's going to give you the weighted mean. Okay? It is not strictly just the average or the mean. Okay? It's taking into consideration the amount of people in each one of the groups. Okay. This graph, or this table here, is explaining how we compute the mean from a frequency distribution table. So think back to last lecture when we developed, or we created the frequency distribution tables. Okay, so far left-hand side, you have your raw scores. So again, the people in your class can score a 10, 9, 8, 7, 6, keep going, right? The middle column there is your F, right? So your frequency, how many people in the class scored a 10? One person did. How many people in your class scored a 9? 2. How many people scored an 8? 4. No one scored a 7, and only one person scored a 6. How I get sum of x is I add up all my frequency. Sum of f is I add up all my frequency. Sum of f is also called n because that's my people, that's my participants, right? So sum of f is n, little n, if I'm dealing with a sample. Sum of f is also n, big N, if I'm dealing with a population. Okay. So f is just how many for each category. Sum of f, or n, is my total count for participants. In this case, 8. And how I got that was I added 1 plus 2 is 3, plus 4 is 7, plus 1 is 8. Okay. F times x, or fx, right? So anytime letters are mushed up or slammed next to each other, you just multiply it, right? So fx, 1 times 10 is 10, 2 times 9, 18, 4 times 8, 32, 0 times anything, in this case 0 times 7, 0, 1 times 6, 6. And then the beautiful E, sum, right? Sum just means add it up. So add up your fx, or your f times x. Okay, so I add up 10 plus 18 plus 32 plus 6, and I get 66. Okay, so I'm trying to, again, compute the mean from the frequency distribution table. So up until now, we're just doing everything we did from last lecture. We're just adding on one more step now in this lecture. Now remember, a couple slides ago I gave you the equation to find the mean. The mean equals sum of x divided by n. And we have all of our bits here, right? We have sum of x, or sum of f, sorry, or n divided by sum of x divided by n, or in this case, 66 divided by 8. And 66 divided by 8 yields 8.25. So if your principal comes in and says, what is the average score for quiz number, 14? And you already ran a frequency distribution and you found the mean, you would say, my class did amazing. In fact, the average score, or the mean, was 8.25. So pretty well. They did excellent. Okay, quick check. A sample of n equals 12 has a mean of 8. What is the value of sum of x for this sample? A sample of n equals 12 scores has a mean of m equals 8. What is the value of sum of x for this sample? I'm asking you just in a little bit different way. So instead of multiplying, you're just going to divide. It's okay. $96. The big takeaway for this one, if you have 2 of the 3 bits of the equation, you can always find the third. Okay? Okay. Messing with the mean. Anytime you mess with the mean, it's usually going to mess with the shape of the distribution. Okay, number 1. Changing the value of any score changes the value of the mean. Meaning, if you go, and I'm going to go back up just really quick. Changing the value of any of your quiz scores, right? So if you say, oh, Jimmy came back and said that this was actually a 4 and not a 9. He just didn't write it correctly, right? So he actually scored a 10 instead of a 9. So now we have 2 scores of 10 instead of 1, and we only have 1 score now of 9. That's going to mess with your average, right? It's going to pull it up. So changing the value of any score changes the mean, up or down. Okay. Number 2, introducing a new score or removing a score, unless the score is exactly the same, is also going to mess with the mean, right? So if you add a new score in, if, I don't know, Susie comes the next day and says, oh, I was sick and I didn't take the quiz, but I'm going to take it now, and Susie's just a rock star and she gets a 10, that's going to pull that average up. But if Susie comes in the next day and was sick and she takes the quiz and she wasn't there like for a week because she was sick, and takes the test and the quiz and gets a 4 on it, it's going to lower the average. Okay. So unless Susie comes in and scores an exact 8.25, right? That was our average, 8.25. It's going to mess with that score, or the average. Okay, adding or subtracting a constant from each score changes the mean by that same constant. Okay? So if you go back through and you say, okay, I'm going to add a half a point to everybody's score because, I don't know, I lopped off part of the question so you really couldn't see it. And that was the printer's fault. And so I'm going to just give everybody half a point. Right? So I'm adding a constant. That's also going to change the mean by that same constant. So now instead of 8.25, now it's going to be 8.75, right? It's going to increase it. Okay. Same thing about multiplying and dividing. Multiplying or dividing each score by a constant multiplies or divides the mean by that same constant. Okay. Quick learning check. A sample of 7 scores, so n equals 7, has a mean of 5. All of the scores are doubled. What is the new mean? So a sample of 7 scores has a mean of 5. All the scores are doubled. What's the new mean? So think constant. The keyword there is all. Right? You got it. Okay. Switching gears a little bit. So up until now we've been talking about mean. Let's do median. Okay. The median is the midpoint of the scores. Okay. So in any distribution, median is the midpoint. As long as they're listed right in order, smallest to largest or largest to smallest, doesn't matter. Okay. Number 2, the median divides the groups of scores into 2 equal sides, right? Half on this side, half on that side. Specifically, the median is the point on the measurement scale below which the 50% of the scores distributed are located, and then on the other side, 50% on the other side. So again, think about taking a piece of paper, dividing it in half, or taking your scores and just saying, okay, that's half. We don't care about outliers. We don't care about really crazy scores, right? Just the median. Okay. We're going to do odd numbers. We're going to do even numbers. Okay, so this first grouping, we're going to do odd numbers. So we have 3, 5, 8, 10, and 11. Okay, first, I was always taught to go lowest highest. So I always put mine lowest highest. So we go 3, 5, 8, 10, 11. Okay. Identify the middle. So if you have 3, 5, 8, 10, and 11, so you take out 3, you take out 11, you take out 5, you take out 10. What's the middle? 8. So 8 is the median. Okay, and so you think, okay, oh, so we'll do even real quick. Okay, so even, again, you can go lowest highest. That's the way I was taught. So now we have 1, 2, 4, 5, 7, and 9. So now we have 6, right? So you take out 1, you take out 9, you take out 2, you take out 7, you take out, oh, now we're left with 4 and 5. So now what do we do? Well, when you take out 4 and 5, you have 4 and 5, or you take the middle of that. So now you take 4 and 5 and you divide that by 2, so you have 4.5. Okay, so you think, okay, what's a real life example of when would we ever do a median versus a mean, right? This is really good when you have outliers or when you have scores that are all over the place. Okay, so think real estate, right? On one street or one block, 1 square mile, you might have housing prices that are all over the place, right? You might have a house that's $4 million. You might have a house that's $800,000, right? So if you are the person who's buying a house or selling a house or a county assessor or we call it like an appraiser, how do you know? How do you know what that thing is worth, right? How do you know what to list it for or what to assess it for or what to appraise it for, right? You find the median. And realtors are really good at this, or marketers are really good at this, and saying, oh, the median house price in this neighborhood is. Because you're always going to have that one person who goes to town on their house and like does all the upgrades and, right, 4-car garage, and it's marble count, everything, right? And then you have the one house that's been there since 1977 and it's never been updated. And you're like, okay, that's fine too. But if you just did the mean, that $4 million house, that $5 million house is going to pull everybody's taxes up, and it's not going to be fair, right? Same thing for like salaries in a company, right? The CEO's salary is going to pull everybody up and be like, oh, everyone's a millionaire. They're not, right? So anytime you have really big outliers, median is the way to go. Okay. Locating precise median in a continuous variable gets a little bit tricky. Okay. Use a fraction. So it's the number needed to reach 50% divided by the number in the interval. Okay, so how you do that is you take the continuous variable, keep in mind the continuous variable, right, that's anything that can be infinitely divided. Time, measurement, that type of stuff. So we're not dealing with nominal or ordinal data. Okay. The precise median located in the interval is defined by the real limits of the value. Sorry. So again, think upper real limit, lower real limit. Okay. And then again, you must determine the fraction of the interval. So look at that thing up there. That you need to do is you divide it by exactly half. Because again, median means half, right? Median, think that thing on the road when it's dividing the road in half, right? You can't cross the median. This process is also called interpolation, and it can be used to estimate an intermediate value when other values aren't really going to be working. Okay, so take a look at the histogram down below there. So you see on the left-hand side where you have that histogram and you see like that gap. This really works well whenever you have a gap with histograms, okay, or fractions or percentages. Okay, so in the previous example I used, like the 4.5, that was a clean one. This is when you have to get a little more precise. Okay, mean, median, and middle, right? So if the mean is the balance point of a distribution, right? So think like a seesaw, right? It's defined by distances, but sometimes it's not necessarily like the exact center of a score. And the median is like the midpoint of a distribution. And it's defined more by the scores, right? So you're getting rid of that one, 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 you're trying to find like the middle score. And it's often not the balance point. What they're both trying to measure is what we call central tendency, okay? What they're both trying to get to is that pure middle. Okay, so take a look at this graph. So population has 6 scores, and you know it's 6 scores because of the frequency, again, so do the count. So you have 1 block, 2 blocks, 3 blocks. So the blocks, right, the frequency, you have 3 people that scored a 2, and you have 2 people that scored a 3, and you have 1 person that scored a 12. You see how that 12 is an outlier, right? So it's a positively skewed distribution. Okay, so it's being pulled over to the right there. Okay. So population 6, right? The mean of 4. So you notice the mean doesn't necessarily divide the scores into 2 groups. In this example, 5 out of the 6 scores have a mean less than the mean, right? So you see the mu there? So if I was to say, what's the center? Do you see how that outlier, that 12 there, is really pulling it over to the side? That's why we have so many different ways we can try to find that middle, if you will, or that central tendency. Okay, quick check. True or false? Is it possible? Sorry, it is possible for more than 50% of the scores in a distribution to have values above the mean. So I'll repeat it. It is possible for more than 50% of the scores in a distribution to have values above the mean. True. More than 50% of the scores in a negatively skewed distribution will be above the mean. So if your brain went to false, you probably were thinking symmetrical, right? That perfectly normal distributed. But are all data distributions perfectly symmetrical? No. If it's negatively skewed, and the opposite is true if it's positively skewed. Okay, next one. True or false? It is possible to have it is possible for more than 50% of the scores in a distribution to have values above the median. It is possible for more than 50% of the scores in a distribution to have values above the median. And if I go too fast on these, you can always push still pause. It is recording, so. False. The median is defined as the score that defines the distribution exactly in half. Again, think of the piece of paper. Think of that thing in the middle of the road for the median. Okay, mode, the last one. Remember, we're going to do 3. Okay, the mode is the score or category that has the greatest frequency of any score in the frequency distribution. It can be used with any scale of measurement, so nominal, ordinal, interval, ratio, any of them. It does correspond to an actual score in the data. That's not necessarily true with mean or median, remember. It is possible to have more than one mode, in this case, bimodal. See how it kind of peaks. It can be trimodal, we don't care, but usually either unimodal or bimodal. Okay. A little talk again about symmetrical distributions. With symmetrical distributions, the mean and the median have the same value. If there's only one, right, if it's just perfectly symmetrical, the mean, median, and mode all have the same value. Okay? And another way, a perfectly symmetrical distribution with only one mode, all 3 measures of central tendency, mean, median, mode, all have the same value. Now, a distribution may have more than one mode. Look at B, right? That's called a bimodal distribution. And to really drive you crazy, a distribution can have no mode. Like C. So a distribution can have no mode and still have a mean and a median. Okay. With skew distributions, the mean is influenced by extreme scores. Okay. With extreme scores, it's usually found far towards the long end of the tail, either positive or negative. Okay. So take a look at A first. In a positively skewed distribution, you see how it goes first the mode, then the median, then the mean. Okay. If you take a look at B, it's also first the mode, then the median, then the mean. I know it looks like I'm reading it backwards, but I'm not. Because how I'm reading is, where does the data pile up? The data is piling up where I'm starting to read the graph. Okay, so over on the right or left-hand side under A, you see how the data is piling up where the frequency is the highest on the far left-hand side, and the tail, right, is trailing off towards the positive end of the number line. That's indicating to me that's a positively skewed distribution. So it goes mode, median, mean. With a negatively skewed distribution, see how all the scores are piling up on the right-hand side? And then, so the mode is still peaking over there on the right-hand side, up, 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 up. And then it goes median, mean. And the tail is pointing towards, is indicating off towards the negative end of the number line. Okay. So if the mean minus the median is less than 0, the distribution is positively skewed. So if you don't like to look at it pictorially and you like to look at it mathematically, you can run a math equation. You just take the number. So if the mean in this case is 10 and the median is 7, 10 minus 7, right? If that is greater than 0, and it is, the distribution is positively skewed. If the mean is 7 and the median is 10, it's less than, so -3, less than 0, the distribution is negatively skewed. So if your brain likes math over pictures, you can run it mathematically too. Also, pictorially, the mode is always found near the short end of the tail, or pointing towards the tail end of the number line. Okay, quick learn check. A distribution of scores shows the mean equals 31 and the median equals 43. So write down these numbers and I'll go back to the previous slide because I just told you the math on it, right? So what do you think it is? Positively skewed, negatively skewed, bimodal, or open-ended? So you know it's either A or B, right? Okay. So distribution of scores, mean equals 31, median equals 43. Again, if the mean minus median is greater than 0, it's going to be positive. If the mean minus the median is less than 0, it's going to be negative. Mean 31, median 43, negative. Okay. How do you go about selecting the central measure of tendency that you're going to want to use? Okay, a couple things to do. Choose the mean if you can calculate sum of x and you know the value of every score. Stay away from choosing the mean if you have extreme scores. If you know you're going to get a skewed distribution, or if you're dealing with nominal ordinal data. Go with median if you're dealing with nominal data. Go with mode. Okay. Go with median if you know you have extreme scores. Again, go back to the real estate example. Go with median also if you know you have skewed distributions, open-ended distributions, or ordinal scales. Go with mode if you know you're dealing with nominal scales, discrete variables, describing shapes, that type of stuff. Stay away from modes if you're dealing with interval data, ratio data. The only time you're really going to use mode is if you're going to, with interval, ratio data, or scale data, is if you're going to use it to accompany, like in addition to mean and median. Quick note on large gaps in data. So take a look at this graph. You see how there's a large gap between like 13 and 100, right? So rather than listing every single data point, what you do is you just do like a little jiggly line there, and that indicates that there's a lot of gap there, because what you don't want to do is just waste paper. So you'll do a couple, like you'll say, even though 13 is the last data point you have, you might write like 14, 15, and then do a little jiggly line, and then go 100. You want to do something that breaks that x-axis. Because what you're trying to do is you're trying to like tell the reader, hey, heads up, we have a big outlier coming. Brace yourself. You can also display means using a line graph. So like think back to last lecture with polygons. It's just a different way of looking at it. And bar graphs. This is usually reserved for, you guessed it, nominal and ordinal data. And you know that because it's got the gaps in between the lines. Okay, quick check. The mean uses all the scores in the data, so it's best to it is the best measure of central tendency for skewed data. What do we think? Mean best used for skewed data? Nope. Remember, because with mean, that skewed data, that outlier is going to pull it. All right, I think this last one. If the mean and the median have the same values, the distribution is probably symmetrical. If the mean and median have the same values, the distribution is probably symmetrical. But just keep in mind, the mode might not be.